Okay, so good morning again. And any questions from the last lecture? Okay, if no, then I just wanted to draw your attention to a couple of things. First, normally students are sending me the emails or messages through Canvas one day or actually the last day when you're supposed to submit the project, right? So if you have any issues with the project, so last day or the deadline day is not the right day to send emails, right? Because you are sending me, let's say someone is sending me a message at 10 p.m. and I'm sleeping at that time, so I can't respond. Second, if you have project related issues, direct them to the TAs first. Okay. And most probably are most of the cases, they will be able to answer your questions because they are the ones who are designing the project. So they don't know more about the project description than me. Definitely we are discussing before they design or they decide the project and its description, but they are the one who are leading it. So they are the right person to contact if you have project related questions. Okay. Uh, Project 3 is released. So I hope you have read its description at least. And if you have questions, you can contact yes. Okay. And if they are not, you're still not clear, then you can contact me. Okay. So last time we were talking about. Now, if you have seen, CPU scheduling topic is taking too long because I guess it is third or fourth week that we are still on the same topic, I guess third week. So we were, according to the tentative schedule, supposed to be covering chapter 9 by now, but we are still on chapter 5. So it's a bit concerning, but then it's fine as long as uh, we are covering the most important topics of the operating systems. We can always offer operating system 2 to cover the remaining topics are, let's say, the more advanced topics. Okay, so we were talking about CPU scheduling, and last time we started talking about scheduling on multi-core platforms, right? And we said that the problem of scheduling becomes more multifaceted when we move to the multi-core platform. For example, either we are going to maintain a single ready queue for all the cores, uh, or we are going to maintain the separate ready queues per core. And also, what are the trade-offs? What are like pros and cons of the each approach? In one approach where we can have the ease of implementation, everyone is going to check the same ready queue. We also have the problem of trace condition, which we can resolve used by putting locks, but then locks result in a lot of overhead. The alternative is to have the separate ready queue for each core, but then it again has its own problem of load balancing where we want to ensure that all the CPUs or all the cores are busy all of the time, ideally, right? So the load balancing is a problem which we need to address in case of the multi-core platform where each core has its own ready queue of the processes. So So what we meant by load balancing was this, if you remember the figure, let's say you have core A, core B, and core C, and each one of them have their own ready queue. And let's say it has 4 processes waiting, it has 2 processes waiting in the ready, not waiting, but they are ready to be run. So they are in the ready queue, they are waiting for their turn to be to get that core, and this one is free. So which basically means that core A has the highest load and the core B has the lowest load. If we assume that all of these processes, they have the same runtime, let's say they are going to complete, and each one of them is going to complete in 10 time units. So after 20 time units, core B will become idle, but this will still be running, and this will still be running. After 30, the core C will also become idle, but its core A will still be have the work to complete, right? So what we want is that we ideally want them to be uh, busy at any given time, all of them, and if any and become free idle at the same time. So which basically means that no code should be staying idle. So how can we solve this problem? We can solve this problem if we ensure that if the core A has relatively higher workload, if we have a mechanism which can check a scan that, okay, which one has the highest load and which one has the lowest load, or even the in between. So you can migrate the processes from one ready queue to the other ready queue. Like, for example, I can assign this one here, and now everyone will have the same amount of workload, right? So there are two mechanisms that, like, let's say not mechanism, the two approaches, but mechanism basically means how to implement the approach. So there are two approaches. One approach is, which is known as push migration, where what you do is that you have a separate task. Let's say I am giving it a name, monitor task. This is not the name given in textbook, but I'm just making up the name. Let's say you have a monitor task. What does it do is that it periodically, like after every certain amount of time, it will go and it will monitor that what is the number of the ready processes in the queue of each core. Okay. And if it finds out that, okay, one queue is overoccupied and one of the queue has lowest workload, so what it will do is that it will simply migrate the process from what the overoccupied ready queue to the queue which is occupied relatively less. Okay, and in this way, you can achieve the load balancing. So we name it as push migration because what is happening is that you're pushing the task from one queue to the other queue, right? And this is the monitor task is doing that pushing, right? The other approach is that what you can do is that instead of push migration, you can do pull migration, where you don't have this monitor task. So actually what happens that, let's say, again, I go back to original example. Let's say this is our occupied. So core B will complete its workload earlier. So when it becomes free, when it has no more tasks, what it will do is that it will look at the queues of the other cores, and then it will pull the task from there, or the process from there into its own. So like this is initiated or triggered by the code. The mechanism or the approach is triggered by the code itself when they become idle. Here, the pushing of the processes is taken care of by a separate task, okay, which is running periodically and every time checking if some queue is overloaded. So this is known as pull migration. The two approaches like push migration or the pull migration, they are not mutually exclusive, which means that you can implement both of them at the same time. So, which can possibly increase your performance. Because it is quite possible, like here we said that it is a monitor task, it runs periodically. Let's say it runs after every 10 time units. It was done here at X time unit and then at X plus 10. And let's say in between here, the core B became idle. So if you don't have full migration, core B will be like waiting for this amount of time before the monitor task assigns or put a process in its ready queue. But if you also have the full migration, so core B, when it becomes idle on its own, it can check the queues and pull a process from the other. Okay. So in this way, like these are just approaches. This is just like we are scratching the surface. They like definitely when you go into more deeper details, for example, how this approach is actually implemented, you will have more questions to answer, right? But for this level of the course, it is enough to know this much level of detail. Okay, so I have explained all this, which is written here, so I'm not going to or maybe I can just read to make sure there is nothing which I'm missing. So in symmetric multiprocessing, we need to keep all CPUs loaded for efficiency. We want to keep them busy all the time. So load balancing is the attempt to achieve that target where we want to keep all the CPUs busy. So push migration is the approach where periodic task checks load on each processor, and if it finds that some of the CPU is overloaded, then it pushes the task from the overloaded CPU to the other CPUs. Pull migration is the approach where an idle processor on its own pulls the waiting task from the ready queue of the other of overloaded processor or CPU. Okay, so now what is the implication of this? What is the implication of, like, we want to achieve the load balancing, and for that we have to migrate the tasks, which means if my task was initially running at core A, after migration. So let me give you this example. So let's say this is the ready queue for core A. Here I have core A, okay, and I have the processor, the tasks or the processes that are going to run on CA in this order: A, B, C, again B, again A, right? So basically, it means that if you, over the period of time, if you take a snapshot, so what is if that first A will be scheduled, then B will, so once it is A scheduled, and after that, when it is retired means when it releases the CA, it goes back to the tail of the queue, right? So this is head, this is tail, right? So which means that, and then similarly, when B is scheduled, after that, when it is done, it will go back. And now then, depending upon the algorithm, the scheduling algorithm, we have all of these ready, but depending upon the scheduling algorithm, we'll pick one of them, right? But the point is that if we are not doing the migration, so if there is definitely what will happen is that if the first CPU burst of A got the chance to run on core A, the next CPU burst will also run on the same core, right? So we know that we have caches in cores, right? And the cores have their own caches, like depending upon the architecture, it is possible that every core has its own private L1 cache and also private L2 cache, or you have only private L1 cache, but L2 is shared with other cores. So let's say that we have a situation where core A and core B, both of them have their own private L1, but then they share L2 cache, right? Now, let's say that we first run core A, or sorry, the process A of the core A, right? And again, I'm taking my favorite example of adding two numbers, C is equal to A plus B. So A is going to do A plus addition of, so it reads the data from the memory, brings into the L2, then it put it in the L1, right? So let's say it read A and B, and it is now sitting in L1, right? And then before it actually does the addition and put the value in C, before it does it, what happens is that it is kicked out from the core, and then it moves at the tail of the ready queue, right? And now before it gets scheduled again on the core A, let's say this monitor task kicks in and it performs the push migration because it's found out that core B is sitting in it. So what it happens is that it puts the process A in the ready queue of core B, right? Now, when a core A wants to run next time, so it needs to access the data A and B, but A and B are now not in its L1. It is in the L1 of the core A. So which basically means that first you need to invalidate this one. Now, how invalidation happens, I'm not going into the details because it is like a totally different topic. But the point here is that invalidation is expensive, one thing. And so first you need to validate the data in the L1 of core A, and you also need to repopulate the data in the L1 of the core B, right? So you are doing two extra things. You are invalidating this one and then bringing the data into the L1, A and B, and then you can do the addition, right? So which means you are paying the cost for the migration. So you are trying to achieve the load balancing, but in the meantime, you also, I mean, as a result or as an implication of the load balancing, you also need to do need to pay the cost for this invalidation and the repopulation of the caches. Okay. So how can now we solve this problem?
Both the L1 and two caches at the same time for A. That way when the gets load balance, it's what have it.
Okay. Your friend said that to solve this problem, what we can do is that when the process A was running at core A and we were populating the L1 of core A, we can also populate the L1 of the core B with the same data so that in future the process A is scheduled here, we have the data already available. Any critique of this approach of the solution?
uh, the other processor core, maybe the cache memory might just not have space, and even if it had, why would we populate something that might have?
Yeah, two issues. Why we do something for which we don't have guarantee? Okay, we are doing the speculation, but let's say what happens, we don't know whether A will be, maybe A completes its execution in the single burst and there is A is never again need to run. One thing. Second, even if we know that it will run again, how we know it will run on the core B? What if it is going to be pushed on the core C or core D, right? So are we going to populate the caches, the L1 caches of all of them? And okay, let's say I go for the extreme solution and I populate the caches of all of them. Then what it means, if I'm putting some data here, maybe it has lower capacity and I need to update some other data, which is needed by another process which is running on the right? So what you can do is that uh, one way to solve or is that you can do the affinity. You can require when you like you can monitor the performance of your system, and if you see that there is too much migration happening because your kernel is trying to balance the loads. So what you can do is that you can restrict the scheduler, your kernel, from putting the from doing the migration. So what you can basically do is that you can say, okay, you monitor the performance of your system for some amount of time, and you saw that okay, process A was ping ponging between core B, core A, core B, core A, then core A, B, C, core A, right? And as a result, your performance was hurt because of this issue. So what you can do is you can say, okay, I want to fix I want to like tie the process A to the core A or to a certain set of cores. So for example, you can say, okay, you can specify and this is known as affinity. So you can specify the affinity of the process A, and you can say process A should always run at core A, or it should always run either on core A or on core B. So maybe like you want to strike a balance where you achieve some level of load balancing, but also you don't want to face too much of problem because of invalidation and repopulation, because at least the L2 is shared. So if L2 is shared, if some maybe the data A and B was already ready here, if it is shared, right? So you don't need to go down to the memory. So yes, you will invalidate here, but you bring data from L2 cache, not from the L1 cache, as compared to the case where you have, let's say, another core C. So this is a single chip, let's say. This is a single chip, dual core chip, and you have another core, which have core C, and it has its own L1 and core B, L1, L1, shared L2, and then memory. So if you migrate the core process A from core A to core D, let's say, it will hurt your performance more. Because here now, when you do invalidation, repopulate, you need to bring the data from memory. Okay. So what you can do is that you can specify the affinity of the processes as there is no such solution which works in all scenarios. But if you find out that, okay, it is hurting my performance too much, maybe I can say, okay, run either on a single process, a single core, or on a set of cores, subset of cores, instead of like all possible set of cores as a candidate. So same thing what I have explained, but let's read the slide now. So a thread or a process has affinity to the CPU it is running due to per CPU cache. So if run in the same CPU, no need to repopulate the cache. Same issue which I explained, right? If for the second CPU burst runs on the same core, most probably, no guarantee, but most probably the data access last time is still there. There is a higher guarantee, higher probability as compared to the case where you migrate it to another core. So what you can do is that you can provide the affinity, or you can specify the affinity. So there are two types of affinity. One is soft affinity, where what happens is that your kernel tries to schedule a given process or a given task on the same CPU for like consecutive CPU bursts, right? But it is just an attempt. There is no guarantee. It still tries to achieve the load balancing, but whenever possible, it tries to run a given process on the same core. Okay. Hard affinity is where you require your kernel and you want it to run a given process on the same CPU, same set of the CPUs all the time. So you can specify the hard affinity, or you can ask your kernel to provide the hard affinity. So for that, in case of Linux, you have an API schedule set affinity system call to specify the affinity of a particular process. So you can actually tell, okay, I want my process here only to run at core 0 or at only core 0 plus or core 2 or core 4 or maybe core 0 to core 4. So you can provide a set of the cores where you want to run your process. So let's say if you provide the set like core 0, core 1, core 2, core 3, these are like possible cores where you allow, then still there will be, it is allowed to migrate that process for the purpose of load balancing between those cores, but not outside of that set. Okay. Okay, so until this point, we have been talking. First, we covered like scheduling of CPU processes in case where we have a single threaded process and we have a single core. Then we talked about, okay, we still have single core, but we have multi-threaded process. Then we talked about, okay, we have multi-threaded processes and we have multiple cores, but those cores are homogeneous. Homogeneous mean they are duplicate copies of each other. Okay. Now there are situations or there are architectures where we still have multiple cores, but those cores are not identical to each other. And there is reason behind that. For example, if you remember last time I explained what it means to be heterogeneous. But why we need the heterogeneity? Why we want those cores to be different? So one reason is to achieve the lower power consumption. One thumb rule is that not always, but typically, larger the size of your core, in like, let's say in terms of logic elements, then more power it will consume. Not always, but this is typically what happens. And so power consumption is a big issue. So what people have proposed, for example, is to use a heterogeneous platform where you have multiple cores, but not all the cores have the same capability, which basically means they are not of the same size. As I explained, for example, maybe one core you have in 8 stages of the pipeline, and another core you have with the 4 stages of the pipeline. Now the 8-stage pipeline will be maybe more performant, but it will consume more power. The 4-stage pipeline line will be less performant as compared to the 8-stage, but it will consume less power. Okay, so one example of this approach is like, let's say this is, I'm naming it as a big core, which has 8-stage, let's say 8-stage pipeline, and you have a little core which has 4-stage pipeline. So now what you can do is that you can use, you can run different type of processes on these two different type of cores. Like let's say if you have processes which are more power hungry, for example, let's say you are running on your mobile the Angry Bird game. So it will be much more power hungry because it includes more graphics, includes more, I don't know, motions. So definitely we consume more power as compared to the case where you have another process, which is a background process, which is doing some maybe some calculating some statistics. Like for example, it is calculating that, okay, what is the total runtime until now for this Angry Bird application. So it is a background. User is not interacting with it. User is interacting only with the, let's say, Angry Bird application. So what you can do is that you can run the interactive application here or the process here on big core, and you can run the background processes on the little core. So which means basically maybe for, and this is like we are saying in my example only one application. What if you have multiple interactive processes which need to be run as scheduled on the same big core, right? And you have multiple background processes. So maybe the criteria you have for these interactive processes is different for the performance criteria for this background processes. For example, you want the response time of these processes to be relatively low, right? So maybe you can use the time slicing. But here, maybe your for the background processes, response time is not the important, is not important for you. Maybe the total waiting time is an important factor, right? So you can use different scheduling algorithm on both. Okay. So we are not going into detail of like scheduling of processes on heterogeneous platforms, but the point here is that the heterogeneous platform may have its own specific details or different criteria or different questions which you need to think about before you decide the scheduling. So in mobile devices, there are little cores, slow CPUs, which consume less power, and big cores, fast CPUs, which consume more power. So what you can do is that tasks are assigned to them depending on their processing needs, like as I just gave an example. So tasks that need high performance are scheduled to the big cores, but they should not run too long, okay? Because if they run too long, then they consume more power. Tasks in the little cores, they can run too long, but they run at, yeah, they can run too long but they are running on a slower processor or a slower core, so they consume less power. Any questions? Okay, so with this is going to be last topic of our last subtopic of our CPU scheduling, and then hopefully we will be done with this. We will move on to the next chapter. So we are looking just an example of how scheduling is performed in Linux, or what scheduling algorithm is used by Linux. So before we start on that, let's have a 10-minute break, and after that we can continue, okay? By the way, I skipped a topic from the chapter, section 5.6. It is about real-time scheduling processes, a scheduling algorithm. Uh, it will not be covered in your exam, but I will strongly encourage you to go and read it and how it is different from scheduling algorithm for non-real-time processes. people who are attending online or who are going to watch the lecture, they have missed this point, this part, because the recording was paused. Okay, now let's go back to the lecture. Sorry that I wasted your break. Yeah. Okay. Okay. So here we are going to look at an example of what scheduling algorithm the Linux is using, not the complete details, but major feature of that scheduling algorithm. Okay. So initially, like the first version of the scheduling algorithm that was implemented, maybe not first, but one of the first scheduling algorithm that was implemented in the Linux, it was called O1 scheduling algorithm because it gives you the constant time for running the or scheduling the processes. But there was a problem with that algorithm because the response time of the processes which are scheduled under that algorithm was not good. So then the algorithm was improved. There was another version in between, but then now the final version which they are using now, default version, is CFS, which is named as completely phase scheduling algorithm. So the feature of the scheduling algorithm is that Linux defines the scheduling classes. So by default, there are two scheduling classes, but if you want, you can modify the kernel of the Linux and you can introduce or add your own scheduling classes. But by default, there are two. One of them is normal processes or the time which are named as time share, also named as time sharing processes. And the other is the real-time processes, the class of the real-time processes. And we have skipped 5.6 section of the book. So the main thing about the real-time processes is that you have hard deadlines. For example, let's say, and they are used in real-time system. For example, you have taken, what is this course? CS273, right? So you have learned the microcontroller. Let's say you are using that microcontroller to monitor the temperature of the room. And based on, like, you put the threshold, like if the temperature rises above this threshold, you need to take some action. And that is critical. Let's say you are monitoring the temperature of your greenhouse. You are maintaining small greenhouse project in your home. And you want to do something. So then let's say the temperature rises above that threshold and you need to take some process, you need to take some action, definitely by running some process, which you want to complete by within certain within certain amount of time. Okay. So in this particular example in greenhouse, if that action is not completed with that certain amount of time, nothing catastrophic will happen. No one will die, right? But let's say if you are in a different situation where if a given action is not completed, it can become fatal. Maybe someone can die. So you have hard deadlines to complete. So hard deadlines to complete an action. So this kind of systems are known as real-time systems, right? Where you have actual hard deadlines of the processes by what time they must complete. Okay. So we are not going into that direction, but in Linux currently they have two scheduling classes, one to take care of real-time processes and one the other normal processes or time sharing processes. Okay, and what they do is that they define the nice value. They have an idea or a concept of a nice value. So nice value is nothing which is defined for every process. So every process has its own nice value. Nice value is nothing but the same thing as similar as priority of a process. So what they do is that they have the nice value, which ranges from -20 to 90. So the lower the number, it means the higher the priority, and higher the number means lower the priority. So every process has its own nice value. Why it is called nice? Because it comes from I was also wondering why it was called nice, but this is the reason why they use this term of nice, because if you have let's say highest nice value, 19, which basically means you have lowest priority, which means you allow other processes to go ahead before you. So you are being nice to other processes. So higher the value, more nice you are. Lower the value, less nice you are to other processes. Okay, so that's why they name it as term it as nice value. So every process has a nice value, and then what uh, completely phase scheduling does is that it defines targeted latency. Targeted latency is actually a period of time. So what they do is that they define a period of time which they name as targeted latency, TM. And then the idea is that all the ready processes in the system, they must they must run in this target latency period at least once. Let's say you have processes A0, P0 to P19, 20 ready processes in the system. All of them must run at least once in this target latency period. But then how much time or what proportion of this target latency each one of them get depends on a different criteria. Maybe P0 runs for, let's say, 5-time unit, and P1 runs for 10-time units, and this next one maybe run for 7-time units, so on. Okay. But how the portion of the target latency is assigned to each ready process, for that they have a different criteria. So for that, what they do is that so here, let's first go through this example. Let's say if there are 5 ready processes and each one of them have equal priority. Basically, the priority is not based on the nice value. It is based on combination of nice value and another factor which they name as virtual runtime. Okay. So, but basically, still you have a criteria on base of which you decide the priority of some of the processes. So let's say if there are 5 processes with equal priority in the ready state, and the targeted latency is 100 milliseconds, then each of those processes will get a time slice of 20 milliseconds because each of them have the same priority. But if they have different priority, depending on that, a portion of that target latency is assigned to them. So in CFS, or completely phase scheduling, they do not assign the priorities directly, and there are no separate queues for each priority class. So remember, they have two scheduling classes, real-time and normal processes. And then in real time, also you have multiple processes, right? And those processes, they also have their own different priorities. And similarly, the normal processes, in the normal process scheduling class, you have multiple processes and each one of them have their own priority. But they do not maintain the separate queue for each priority level. Okay, they have single priority queue, a single ready queue. So what they do is, for the purpose of the priority, what they do is that they keep track of how long each process has run as virtual runtime. So virtual runtime is different from the actual runtime of a process. So actual runtime is like how many CPU clocks it consumed, right? So, but virtual runtime is different, for which they have a certain algorithm to advance the virtual runtime of a process. But I mean, I am not aware of that, and I haven't tried it, and we are not going into that direction. As I said, we are not going to cover the complete scheduling algorithm, but the major features of the scheduling algorithm of the Linux. So what they do is that they advance the virtual runtime of low priority processes more or comparatively in a faster rate as compared to the virtual runtime of a higher priority process. So let's say, here's an example. Let's say 200 milliseconds, the actual runtime will be more for low priority process and less for higher priority process, and same for nice value of 0. Okay. So will be more basically mean that if our process has 200 millisecond actual runtime, but it has lower priority, then the virtual runtime of that process will be higher as compared to a process which also has 200 millisecond of actual runtime, but has higher priority. And even if both of those processes have the same nice value. Okay. And then for the purpose of the scheduling, what they do is that they first select the process. Let's say, like here, I gave you an example. Let's say you have 20 ready processes, which need to be run in this targeted latency. Each one of them will get a portion of this target latency, but which one of them will be selected first? It depends upon the virtual runtime. The one which has the lowest virtual runtime will be selected first for execution, but then how much amount of time it will get to execute will depend upon its priority, which is nice value. Okay. Any questions? Okay. And what they do is that, remember, what until now what we were considering that there is a list of there are multiple ready processes, and we are maintaining them in a queue, ready queue, right? And we were implementing that ready queue, let's say, through a linked list where we are maintaining the tail and head. Okay. But in the CFS algorithm, what does it do is that instead of implementing the queue, it uses the red-black tree to maintain or to handle all the ready processes. So red-black tree, it is a balanced tree, one thing, and it is a binary tree. So, and it is sorted. You have taken the course on data structures, and you are aware of what does it mean to be for a tree to be balanced, binary, and sorted, right? So basically, what it means is that they are the process with the smallest value of runtime will be the extreme left node of at the lowest level, left node of the red-black tree. And the node on the extreme right in the lowest level will be the process which will have the highest value of the virtual runtime. Okay. And what did we say? That the CFS, when it schedules the processes, it picks the one which has the lowest runtime, virtual runtime, which means the most left node of the process of the tree. So what they do is that when they implement the algorithm, they always put the most left node in the cache. So it is always cache, mean it is always close to the core, closest to the core. So since they are maintaining it in the cache, they don't need to go down to the memory every time. So what happens is that they need to pay the low latency to access this element or this node of the tree, right? And every time so this is the tree of only ready processes, not all the processes, only ready. It's for processes, let's say ready, and then let's say you get this process, you schedule it, and then it needs them to do an IO, which means it is no more ready to run. So it is not put back in the ready tree, red-black tree, it is put in the list of or in the set of the process waiting processes. So which means that it is removed, the node is removed, right? And when it becomes ready again, you need to put it back in the red-black tree. So you need to do insertion and deletion operation on the red-black tree, right? So, but the advantage of maintaining the ready processes in the form of the tree is that you can access it in a constant time because you are always putting it in the cache, maintaining it in the cache. And whenever you need to do the insertion and deletion, don't need to scan the whole queue because there is no queue. So you can scan it, do the insertion and deletion in O log n time. Okay. Yeah, I think I have explained same thing which is written on the slide. Any questions? No? Okay, if no questions, so maybe then we can finish early today. Okay? Because that's all I have to share today. Thank you.